Dear students, welcome to this massive open online course on operating systems. Today we are going to discuss about system call implementation and process scheduling in x86 environment. So, we have already discussed about how x86 operating system, which is done by MIT, is used for educational purposes in creating commands in the x86 environment. Now, we are going to see about system calls can be created in x86 as well as how process scheduling concepts can be implemented in x86 systems. So, the objectives are to understand about the various system calls, to learn how system calls are implemented in x86 and how we trace the system call execution flow. Understand the role of process scheduling, that is the new process scheduling concepts can be included in the x86 and understand the context switching that is happening in x86 during process scheduling. So, basically before going to the implementation of SV6, we will see how SV6 has accept the system call and how it is implemented. So, it is an interface between the user program and the kernel and it allows the controlled access to hardware resources. So, as we use system call which is generated by the application program for performing some task, we have to give proper access mechanism and controlled access mechanism for the system calls generated by the application programs. Different system calls like create system call, which is done for process creation, then handling file IO input and output, then allocating memory spaces, we use various system calls. So, these system calls we can implement in SV6 and test how it is working. More importantly, the restriction for system call privilege in this environment is to protect the OS as well as to enhance the abstraction between the hardware and the actual user application program. Why these calls are needed? So, the user programs run in restricted mode. So, direct access to hardware is not safe. So, we have to give only the privilege for the application program with a lesser level when compared to the kernel level. So, kernel validates and executes requests. So, it ensures the security, stability and resource management. So, we have to give the provision for the kernel to have all these features like security, stability and resource management, even though the system call is initiated by the user application. So, generally how system calls will flow, it is the user program invokes the system call, it traps into the kernel, seeks the permission of the kernel for carrying out the task and the kernel identifies the system call. According to the system call, it will contact the respective device driver for carrying out the task, then the kernel executes the service. So, we have various kernel services, all the services will be executed by the kernel and controls the return to the user program after completing the execution of the call. In the diagram, you can see that user process is executing instruction and we have the system call which is calling for some service. As soon as it is called, the user mode is generating a trap that enters into the kernel space and the kernel will execute the system call by as per the call which is generated. It may need the device drivers to be invoked, it will do all this and after completing this it will return the result to the user mode. This is the diagrammatic flow of a system call flow. x86 system call architecture, it is very simple and minimal in design. It uses trap mechanism as I said to enter into the kernel space, then system calls identified by numbers. So, all the system calls are represented by numbers. So, when you create a new system call, you have to assign the number for the system call and we have the clean separation of user and kernel code. So, only by trapping into the kernel it will give it will get the access from the kernel. So, as we discussed about trap mechanism, it is a system calls uses a software interrupt. It is an asynchronous interrupt generated by the user program. As soon as it is generated, that it the CPU switches into the kernel mode. So, via this trap it switches into the kernel mode, then it saves user context. As soon as it enters into the kernel mode, it handles using the trap handler. Then after completing the job, it will leave the kernel mode and again it resumes the execution, further execution in the user mode. So, system call entry in the x86, the user program executes the syscall. This is the one important instruction called syscall, system call we call by using syscall instruction. So, it executes using that call, system call number stored in this register, arguments passed via registers and stack. So, for system call you can pass some arguments, these are all passed via this register. Control, once it is done, the control is transferred to the kernel. So, this is the system call. It says that it has the system call number, that is 4, 5, 141, 142 and this maps the system call number to the handler function which is responsible for handling the system call. So, we have 141 and 142. 142 is for sys/select and 141 for sys/getDens. So, this is the handler function. So, it enables easy lookup and dispatch. So, this number and this handler function is just a lookup process and dispatches the corresponding signal handler routine. So, as soon as it is done, then everything is controlled by the central point, that is the system call table contains the entire list of all the system calls and the corresponding signal handler. Passing arguments, the arguments passed from the user to the kernel. So, the kernel will retrieve using the helper functions and the kernel validate the arguments whether these arguments are appropriate for execution. Then it checks whether it is crossing any memory boundary. So, it is prevent invalid memory access. So, the kernel is responsible for ensuring that the arguments are correct and it is not crossing the boundary to access any resource. So, if you want to implement a new system call, these are the basic steps we have to follow. The first step is to define the system call number. As I said, we can create a system call number using a function like hash define the system call name, and you can declare some number like 22. In this name you can specify any user defined name you can specify. For example, if you want to have a system call for computing the date of an year or finding date of a year, you can call sys/year. So, this you can include in the program. So, declare the handler. So, the kernel handler will be responsible for handling the system call where it contains the code. Add entry in the syscall table. So, in the syscall table you have to enter the value which consists of we can see here we have the number and the handler. So, likewise we have to add that. So, add entry in the syscall table, expose interface to user programs. Now, the interface is exposed to user programs once everything is assigned, then you again rebuild. This rebuild will is used for again executing the code based on the updations we have made. So, if you add a new system call, we add the system calls. For example, these are the system calls they have added, and if you want to add few more system calls, you can add here. This is system call and this is the handler. So, if you add this, it will call the appropriate handler function, and you have to write code for what actually you have to do. So, the kernel side we have to write the logic for the system call. For in this example, they have written code for two system calls, one is hello and another is fork. So, hello what it should do, it do this process of printing, and fork this sys/fork will do the return of fork system call. So, it calls the fork function, it returns the value. So, this is the actual core logic written inside the kernel. So, it can access the hardware and kernel data for giving the results. So, this must be handled without any error, and the result is returned to the user. So, this is an example for creating two system calls sys/hello and sys/fork. So, if you appending this, you have to again rebuild and you have to execute. Suppose if you want to add another system call, then again you can open this, you can update, and again you can rebuild, and then you have to compile and execute. So, the user level programs called wrapper functions. Wrapper functions are add-on functions apart from the basic functions. These wrapper functions can be used for triggering the kernel trap to enhance the system calls functionality by calling the respective driver software if necessary to give the output as per the system calls requirement. So, here we have the various things added, and it mimics the basic Unix programming model, and it simplifies the usage of applications. So, the user level access to system calls is very minimal, only they can call wrapper functions and it can trigger the kernel trap. For that it is responsible for triggering the kernel, and the kernel will take over the job of providing the service. So, it simplifies the usage of applications for executing the system call. So, the kernel will take care of this. Similarly, if you want to create a process, for example, if you want to process to the x86, we can have a scheduler. Every scheduled entity in XV is represented by the structure. So, we have the process, and it has various take like page table, kernel stack, process state, process ID, parent process, context for context switching. So, all these things will be represented by a structure. So, it is represented as a process table also. So, process table in x86 is all the processes stored in the global process table, and this global process table will represent the list of processes. It is a fixed size array, and the kernel, this is the fixed size array, and the kernel will scan table to find runnable processes. So, here we have the process table entry which is having log, and this is the entry which is added. Simple but inefficient for larger systems. So, for large systems we have complex implementations. For creating such thing in complex system is always inefficient. So, for understanding purpose of how process is handled, you can use this type of mechanism. So, various states in XV6, we have the process state, we have unused state, and all this represents the different states of process in the XV6 environment. And the transitions, a process will have so many states, and these states will be transiting from one state to another state based on some events happen. So, here we have the process runnable to running, then running to sleeping, then running to zombie. So, these are all examples of state transitions in the process. If you look at the XV6 scheduler, the XV6 scheduler implemented as an infinite loop continuously look for runnable processes. So, it keeps track of all the states of the process, and it keeps a runnable process which is ready for running. So, when the process is ready for running, then it selects one process at a time for allocating the resource. So, it gives CPU control using context switching. Hope you all know about context switching. It is one execution, and if there is any process schedule which is having higher priority, then it will be switched over to the new process. So, here the scheduling algorithm used basically in XV6 is round robin algorithm. So, you can use round robin algorithm, round robin scheduling, and each runnable process gets CPU in turn. So, we all know that round robin how it works. So, a particular quantum of time is allocated to the process by the CPU. After timer get expires, then this process will be put in the queue. So, it has to get the second turn or another turn for the remaining execution. So, likewise as per the quantum time, it keeps on revolving in the chain. So, this is the basic process implemented in XV6. So, there is no priority concept in SV6. So, equal time sharing and simpler and fair for smaller systems. So, this is the scheduling algorithm which is implemented here. You can see here it is checking whether the process state is equal to runnable. So, if it is runnable, it is checking in this list. These are the list of states we have created, and it is checking whether the given process state is runnable. If it is, then the CPU will be given to this process. So, order of process table, scan, round robin scheduling. So, every process will be scanned, and it is assigning each process when the process state is equal to runnable. This is how scheduling is done in XV6. So, during scheduling, we know that context switching will happen. So, context switching is switching CPU from one process to another process. So, during this process, no actual activity which is giving the outcome to the throughput is happening, but too much of context switch also will degrade the performance of the system, we all know. So, during that process, it saves the current process state and restores the next process state. So, the current process state will be saved, and after coming back again or while resuming the task, uses that state. So, this is performed by the kernel scheduler. So, this is the main role of a kernel here in this context. So, if you look at in the kernel point of view, this is the kernel stack of the old process and the kernel stack of the new process. So, context of the old process, then whenever the service request arrives, it switches over from this to this, and after completing this again, when the context is switched, the context will be given to the new process, and after this again it can resume back to the old process. This is the basic context switch, that is what happening during the round robin scheduling happening in the XV6. So, if the quantum time is less, more number of context switch will happen if the amount of time required for the process is more. If the amount of time required for the process to execute is less, of course, the number of context switch will also reduce. So, during a context switch basically follows a structure where it saves the values in the program counter, stack, pointer and registers. The XV6 has the minimum state saving for simplicity. Now, in generally context switch saves few more parameters about a process. We call it as the term called PCB, we call it as process control block, which contains more parameters to be saved. But here we have a simplified version of context switching. So, it saves only the 3 parameters: program counter, stack pointer and register values for our learning purpose. The role of timer interrupt, here the timer interrupt triggers the preemption. So, as and when the quantum time gets over, it triggers the preemption. Preemption is nothing but revoking the job back, process back from the CPU and assigning the new job to the CPU. A single process is not running the CPU forever. So, it forces the scheduler invocation and enables time sharing. So, this is how a fairness is assigned, followed in the process scheduling. So, this is the process scheduling in SV6. So, during this process we have the normal conventional things happen like sleep and wake up mechanism. So, where The process sleeps while waiting for the events. CPU released for other processes. The process will move from other state to runnable. So, now it is ready to be assigned the CPU. So, the sleep and wake mechanism is helping the process to sleep when waiting for some events to happen, and CPU release for other process, and wake up will enable for moving the process to runnable state, thereby the process can be assigned to the CPU by this round robin scheduling algorithm. Scheduler uses logs for safety. So, as we all know that whenever it is doing some scheduling task, it is not be affected by others. So, we perform locking. So, it is again a synchronization type of mechanism. So, the scheduler during this process, it enables lock for safety to prevent race condition competing more at the same time. So, it ensures the consistency in the process state, and it is very important in case of multi-processor environment systems, where multiple processes will be having processes running at the same time. So, logs ensure safe concurrent access. So, whenever we call acquire and lock, then it is done, then after completing we will release the log by calling the release function. The same logic applied here. So, what is the strength of this XV6 scheduling? Even though it is very simpler version of normal scheduling mechanism, even though we follow the logic of round robin. So, it is extremely simple design, easy to read and modify. It is ideal for understanding core concepts of the scheduling and minimal abstraction overhead. So, it is giving us the exposure to work at the kernel level. So, basic limitations of XV6 scheduling is there is no priority for XV6 and no advanced scheduling policies can be implemented. It is inefficient for large number of processes. So, not suitable for production systems. So, we implement SV6 scheduling for the purpose of learning, but in terms of production point of view, this operating system is not applicable, it is only for learning. So, we can go for Linux for production states. So, when you compare with modern OS scheduling algorithms, XV6 uses simple round robin as we discussed just now, and there is no priority handling. So, modern operating system, as we all know that processes will be coming with lot of priorities, and we have to give access to our CPU with based on the priority. We can follow multiple level queues scheduling, load balancing for various queues, all those stuffs. So, these kind of complex functionalities are not supported by the XV6. It is basic version for learning purpose. What we have discussed so far is about what is the purpose of XV6. It provides a clean learning model to learn about the internals of the operating system in terms of kernel space, how user applications interacts with the kernel, how the various resources or access privileges for various resources are handled effectively by the kernel without giving too much of the provision for the user space, and the various system calls we can implement in XV6 by creating user defined system calls and writing the code and embedding the code in the program file, thereby this can be rebuilt and again you can invoke. So, you can have a list of changes we can make, and all this can be again rebuilt and execute again for having the effect in the outcome. If you go to the scheduling part, the scheduler is selecting the appropriate process to be scheduled, and it switches from the older process to new process to assign the resources to the newer one. XV6 is helping in understanding about the scheduling of the process and how the efficiency can be improved if the scheduler is scheduling with of course with minimal provisions. So, this presentation hope it helps to understand how XV6 builds strong OS foundations in terms of learning the various operating system concepts, and also you can develop few more additional implementations to learn much more concepts of the operating system. So, there are various resources available in the internet. In the MIT website itself, you can find how XV6 can be downloaded, and how various exercises, tasks we can perform over the XV6 in the form of assignments and lab exercises. So, I think this presentation is useful for you to learn about the operating system concepts under using this XV6 operating system, which is basically for learning purpose. So, with this I am concluding this presentation and hope you all enjoyed listening this. Thank you.